Hello everyone, welcome to this session where we'll dive into the concept of biasing in bipolar junction transistors or BJTs, specifically for the three primary configurations: base bias or fixed bias configuration, emitter bias configuration, and collector bias configuration. For the definition of biasing, we'd have to know that it is an essential process that ensures that a BJT operates in its desired region of operation, typically for the purposes of amplification. Without proper biasing, it may even happen that the transistor may not function correctly, leading to issues like distortion or even complete failure of the circuit. Proper biasing ensures that the transistor operates in its active region where it can act as a reliable amplifier. Without biasing, the transistor might even be stuck in cutoff region where no current flows, or saturation where maximum current flows through the transistor. Operating points are of two types because of two pole switching transistors. One of input operating point, that is the intersection of the load line with the input characteristics for particular output voltage. The other of output operating point, the output Q point, that is the intersection of the load line with the output characteristics for particular input voltage. As we can see, the circuitry for the same is something like this. First of all, this is at the input side and this is at the output side. What does it show? It shows that a certain particular signal has been amplified by some magnitude on the output side, which shows that how this particular bias configuration has been used for the purpose of amplification. For the traces of the load line, we see here that a graph has been plotted, that is IB, which is in magnitudes of mu ampere, versus VBE. What is IB? IB and VBE are the input characteristics for this particular biasing. We have graced the first point here. Now this equation, where does it come from? It comes from here. Plus VBB minus of IB into RB minus of VBE. Since this is a complete loop, the voltage equivalent would be 0. Hence this is equal to 0. Point 1 is the point on the y-axis, which denotes the IB for this equation. For the equation of IB, we see here that VBE has been denoted as 0, which is quite obvious from this graph. And for point 2, which is this point, that is the plot of that is the plot of the voltage VBE, that has been plotted when IB is equal to 0, which is again obvious because of the graph viewpoint. Now the intersection of the load line with the particular input characteristics, what does it mean? This means that this graph, when it intersects with the particular load line, this is a load line, this is a load line as well. This can be denoted as LL1, LL2, LL3, or the nomenclature could be anything one desires. Now the intersections means these points Q1, this might be Q2, this might be Q3. Now the slope here is minus 1 by RB, and these are the very operating points or Q points or quiescent points that we define. Now another important point about this is that the Q point should be in middle, because if it is near cutoff or saturation region, then distortion will take place, which has been stated before, that without proper biasing, that distortion might take place, which may even destroy a circuit. Now how does this come about? Now this is a particular biasing graph. Now this is the output characteristic one, and here we can see that that various Q points have been plotted here. This is Q2, this is Q, this is 1. Now the thing with this is, for instance, if we take Q2, here the AC graph AC plot that has been made, we can see that some bit of it has been plotted outside the perpendicular drawn from here. Now what does it say? It says that this has more current, which is not plausible for it. Therefore it is not valid. Now Q1 on the other hand, the AC plot for it is particularly shown in a way where it shows that this has more voltage than VCC, which again is a problem for the circuit because it would always destroy it, since output voltage is either less than or equal to VCC. Now the particular point denoted as Q lies somewhere in the middle, or if not, roughly a bit to the left or right. Now this, when the AC has been plotted, we can see that there are no extras either on the left or on the right, which denotes that it is particularly the most convenient point one could find for the operation, or denoting it as the operating point. So this will be our most convenient quiescent point or operating point. Now moving ahead, we move to the exact topics that we need to explore in this video, and one of the three is fixed bias configuration or base bias configuration. The components required for this circuitry, which is roughly equivalent to the one we need to configure in this session. The components would be power supply, that is VCC. What is that? That is the power. That what does it do? It provides the required DC voltage to power the circuit. VCC exists here to provide the required DC voltage that would power the circuit in this circuitry. Now base resistor RB, it is connected between VCC and the base terminal to control the base current IB. Now the IB flows from here, and this is particularly RB, which has been denoted here. Now a transistor, it could be NPN type or PNP type, NPN or PNP BJT, which operates as the active component, obviously, that we all know. Now for the purpose of its operation, how does it operate? Now there have been two coupling capacitors that have been connected to this circuitry, one at the input signal, one at the output AC signal. These capacitors are replaced by open circuits because of their infinite resistance, which is the most convenient method of approach on any kind of circuitry that we come across in our lives. Now the resistor RB, which provides a base current IB to the transistor. For a silicon transistor, the base emitter junction, that is this junction particularly, needs to be forward biased, requiring a voltage denoted as VBE of approximately 0.7 volts. And if there were a germanium transistor, then the same would go down to 0.3 volts. Now once the base emitter junction is forward biased, a small current flows through RB into the base. Now a small current flows through RB into the base. This base current determines the collector current through the relation IC equals beta IB. Alright, and this is the particular relation that we established from this equation. So for the derivation of these equations, what do we have to do? We just have to apply Kirchhoff's rule, or even just voltage equivalent laws to determine the voltage IB and place these into the particular relations. One relation that needs to go as prerequisite is that IC equals beta IB. Right. Now this beta is also termed as amplification factor or current gain factor. Yeah. So for the derivation of these equations, we start from either of the circuit. We can observe either of the circuits. I'll go with this one because the arrows have been denoted in this one as well. So plus VCC minus of IB RB minus of VBE equals 0. How do we approach this? We approach this in this particular manner. Plus VCC minus of IB, only IB flows in this, and RB. This is RB, which has not been denoted here, but yeah, this is RB plus VCC minus IB into RB minus of VBE. This is VBE equals 0. Now since this is a complete loop, the voltage equivalent would be 0 because in a closed loop it's always 0. From this we can derive an equation for IB in terms of VCC, VBE and RB, where VBE would mostly be approximately equal to 0.7 volts if it is mentioned that it's a silicon transistor, or if there's nothing mentioned, then we take the standard case for a silicon transistor. Now IC equals beta IB, from where we can export this equation that IC equals beta VCC minus of VBE by RB. Now VCC minus IC RC minus VCE equals 0. Right. So where does this equation come from? It originates from here. Plus VCC minus of IC RC minus of VCE equals 0. Why does it equal to 0? Because we can see that the circuit has been grounded here. So since the circuit has been grounded, we can see the voltage equivalent would obviously be 0. Right. Now if we need to observe from this direction, on this circuitry as well, we can see that plus VCC minus of IC into RC minus of VCE equals 0, since it has been grounded, and since it's a closed loop, we know that the voltage equivalent would be 0. Now this is the particular configurations for fixed bias configuration, and there are few theoretical points about it which are particularly very important for our convenient day-to-day lives. So few advantages of this configuration include that it is simple to design and implement, and that it requires only one register. And what was the name of that register? We denoted as RB. Disadvantage for this may be that the Q point instability. The operating points depend on the transistor's beta, which can vary significantly with temperature, as it is temperature sensitive, which has been explored in this point as well. That as the temperature increases, beta increases, causing the collector current to increase, which might push the transistor into saturation. And there are a few very limited applications for this. That is, poor stability makes it unsuitable for high performance or very high precision circuits. Its applications include that it is used in basic or low cost circuits, which is because it's a very fundamental setup for any kind of circuitry. And this basically demonstrates the importance of BJTs, and it is a leading example of the fundamentals of BJT operation. Now moving on to the next topic, that would be emitter bias configuration for us. The circuitry for this would is supposed to look something like this. It is basically just as similar to base bias, but the only difference is that the addition of RE, that is the resistance or the emitter resistance we call it, from fixed bias, and that is done only to enhance the stability from the base bias relatively. Now a few points stated about it could be that the emitter bias is a more stable biasing method compared to base bias. It provides good thermal stability and ensures that the transistor would surely operate in the active region so as to attain the most convenient and optimal quiescent point. So for the derivation of equations, we can move in other directions, either from this direction or from this direction. We'd get different variables and encounter different components while we move across the circuit. As I said, the only addition has been that the RE has been added onto the circuit, which has been connected directly to the ground. Now, for the derivation of the equation, we move ahead. That is VCC minus of IB dot RB minus of VBE, that is this right here, minus of IE into RE equals 0. Now, a relation that we all know is that IE equals to IC plus IB. That is, the emitter current is equal to the collector current plus the base current. And we know another relation, that is IC equals beta IB. Hence, this has been replaced here as IC equals to beta IB plus of IB, which in all becomes that IE, that is the emitter current, directly equivalent to beta plus 1 IB. What's beta here? Beta is still the same variable, that is the current gain factor or the amplification factor. Now, VCC minus of IB RB minus of VBE minus of beta plus 1 IB RE equals 0. Now, it is this very equation that has only been replaced by this forms of the equation that we have already derived. That is VCC minus of IB RB minus of VBE minus of beta plus 1 IB RE. Now IE equals to beta plus 1 IB. Hence, this has whole been replaced by beta plus 1 IB RE. Why has the resistor has been added onto this? Now the reason for this is pretty obvious, as I stated, that the emitter resistor introduces negative feedback onto the circuit, helping to stabilize the operating point to attain a more convenient and optimal Q point. This negative feedback features include that if the collector current increases due to any such change in variables, such as the temperature variable, which we treaded upon in the previous part of this video, that is in base biasing, how the temperature variation and the variation in beta was one of the very disadvantages of the base bias, if we recall. So that very fact has been stated here, that in this, if the collector current increases due to temperature or any other factor, IE also increases, which in turn increases the VE, since VE is directly proportional to IE, and VE equals IE dot RE, which in turn reduces the VBE here. If VE increases, that is this very part here, then VBE would in turn decrease, which would be the only key feature for the addition of RE, in addition to the attainment of the better Q point. So we were right here, VCC minus of IPRB minus of VBE minus of beta plus 1 IBRE equals 0. Now, as we can see that for the sake of the simplification of the math here, we use VCC minus of IB. We take IB common from out of all this. RB plus of beta plus 1 RE. The negative has been taken in common here. Minus of VBE equals 0. IB equals to VCC minus of VBE by RB plus beta plus 1 RE, and IC equals beta IB, which is the standard equation that we all know. Now, this is nothing new. This has only been derived from this equation to write here. VCC minus of ICRC minus of VCE minus of ICRE equals 0. Yeah, I just faced a little bit of network issue. Yeah. I bet the stream is not lagged. Yeah. So VCC minus of ICRE minus VCE minus ICRE equals 0. Where does this come from? This comes from this part of the circuitry. Yeah, this part of the circuitry. We move from here. VCC minus of ICRE minus of VCE. So what's VCE? VCE is this very part here. VCE, this across this whole terminal, whole NPN transistor. VCE minus of IC into RE, minus of IC into RE. Now, how is IC the same? How is IC here and IC here? The only part of the division for current is happening only here. This is where IB flows from. This is where IC flows from, and this is IE in itself. So yeah, this is VCC minus of ICRE minus of VCC minus of IERE equals 0. And IE is almost equivalent to IC in this, which is why this very equation has been replaced by IC, where IE has been cut off to IC. So VCC minus of IC, RC plus RE minus of VCE equals 0. How does this come? This comes from this very part where we almost take IE equals to IC, that is the emitter current has been taken as equivalent to the collector current. So all in all, the equation for this becomes VCE, that is the collector emitter potential difference, is equivalent to VCC, that is the collector potential, minus of IC RC plus RE. This is basically the equation that is needed to solve any complex numericals or circuitries based on this particular configuration. And yeah, this is pretty much all about the circuitry that is involved in emitter bias configuration. Advantages for this emitter bias configuration would include improved stability, which has been the primal factor for us to opt this very configuration. Then there is improved stability has been justified here, as since the emitter resistor provides negative feedback, it stabilizes the operating point, which has been explained in this that there is a better convenient approach to the thermal variation that occurs in base bias, and in emitter bias we do not face that very problem. And since this is the same very fact that the reduced dependence on beta, since beta is very thermally sensitive, the IC varies, which in turn varies the VCE, which in turn varies the VBE. And since in this configuration it is very less dependent on beta, that's why it is a better option for us. Now, a few disadvantages would include that the lower voltage gain, which says that the emitter resistor reduces the voltage gain due to the voltage drop across RE. The voltage drop across RE is heavily reduced in emitter bias configuration, and it requires dual power supplies. Often requires both VCC and negative VEE power supplies for effective biasing, although this can be simplified in some designs. Now, this very fact was never used in base bias configuration because there was only one power supply that was needed, which was VCC in itself. And here we need to opt for VEE, which is the negative input, a negative power supply here. And due to this that simultaneous dual power supply, it could be a very optimal disadvantage in this very case. Particular emitter bias configuration of transistors is used in amplifier circuits, and also it is very highly suitable for high performance and stable designs in complex circuitries.